The picture depicts planet Earth and man, the Lord of creation, standing on land. Water runs off to the oceans under his feet as he racks his brain over the causes of climate change and disasters he must face with increasing frequency. Droughts, floods, landslides, streams dry up, river and groundwater levels drop, landmass overheats, atmosphere overheats. Here is a graph of climate change effects. In this NASA animation, which illustrates temperature measurements between 1880 and 2011, reds indicate the mean air temperature rise since 1850. If the temperature around the equator rises by 0.6 degrees Celsius, the temperature at the North Pole increases several-fold. In this graph, blue illustrates the minimum water levels of the Uch and Tisza rivers in millimeters since 1956 and the parallel estimated drop of the groundwater levels. Some sources claim that the greater vaporization brought about by climate change is a cause of rivers drying up and river and groundwater levels dropping. For several decades, nature has been central to my work, as it has revolved around building forest roads, levees along rivers, and logging. My continuous experience with water and soil has helped me realize that there are three unequivocal causes for the dropping river and groundwater levels, and by extension, for the desiccation of streams and forests. Namely, these are as follows: compacted soil areas, even at minimal grade, especially in the forests, that expand thousands of kilometers each year. Man-made slopes over compacted soil areas, we disrupt billions of soil capillaries each day. Drainage canals and lowlands. All three interventions might seem inconspicuous in themselves, yet they sprawl astoundingly fast and set off a disastrous process. They drain the landmass, which in turn overheats. Compacted soil areas. Most commonly, they are created by heavy machinery operating in intact forest vegetation, mainly during timber harvesting on forwarding paths. During log skidding, one forest tractor can compact up to 3 kilometers of forest soil, 3.5 meters wide, or 1 hectare in a single day. Rainwater or meltwater cannot infiltrate the compacted soil and reach the plant roots, springs, and groundwater. Instead, compacted soil routes the runoff water swiftly to lowlands and subsequently to oceans. In recent years, soil compaction and forest drainage has accelerated multifold. We have significantly increased the use of wood as a renewable source of energy in supplying the wood chips to the heat and power plants. When the logging process is complete, no one is charged with the task to restore the compacted soil to ensure the rainwater can infiltrate the soil once again. And yet, soil in this condition does not produce any vegetation for decades to come. To compound this effect, it also intensifies the runoff, which in turn strips the topsoil. All that remains at the end of the process is eroded rock that reduces the chance for new vegetation to a zero for several centuries. Here is another example. Soil that was compacted 50 to 80 years ago during horse skidding is covered in a 30-centimeter layer of rotten leaves and wood. Rainwater or meltwater still do not infiltrate the ground. The volume of runoff from rain and snowmelt increases due to the sprawling slope compaction, especially in the forests. The forest will lack the water in springs and summers. This scene shows intact forest soil that does not get soggy even during rain or snowmelt. I have been monitoring the condition of the Carpathian forests in the Ukraine and in Slovakia for several years. I have visited many places in Europe affected by floods, including the Polish forest, Jezirskie Hory in Bohemia, and the mountains over Genoa, Italy, near Dublin, Ireland, in Macedonia, and in St. Lawrence in the Austrian Alps. Lately, I have been to Lourdes in the French Pyrenees that had been hit by a flood. I was surprised to find a dense network of forwarding paths in the forest there. What caught my eye even more was a 10-kilometer asphalt road that stretched above the tree line, across a grassy area, and finished under cliff formation. High, man-made slopes above the road drained the mountain readily, as we witnessed when we got caught in the rain. The rainwater from the capillaries flowed out through a roadside ditch to the valley, then the rivers and the ocean. Again, I saw for myself that compacted soil and the slopes above them cause rapid landmass drainage. Man-made slopes. As we make artificial slopes, we disrupt billions of capillaries, which store enormous amounts of potable water and function as distribution channels to groundwater systems, springs, all plants. The water that flows out of the capillaries oozes down the compacted soil or a ditch under the slope. Drained capillaries in the slope are like ruptured supply pipelines which cannot serve their purpose. Human intervention in the landscape has turned the natural system that is meant to retain water into a drain pipeline, which causes the landmass to desiccate instead. The disrupted capillaries channel the water from rain and snowmelt instantly from the landmass to the seas and oceans. Topsoil in forests and forest meadows filter water from rain and snowmelt readily to the capillaries in deeper layers of the earth. For this reason, forest soil freezes only in places that were compacted by heavy machinery and human activity. It is clearly visible near the log yards in the meadows. Here you can see how much meltwater flows through the soil filter in the capillaries. If we sever them, they will discharge water, which will flow down the forwarding path or the ruts carved by the heavy machinery. The same process takes place during sustained or heavy rains. The compacted soil drains the rainwater instantaneously, compounded by water discharged from the severed capillaries, much quicker than during the snowmelt. Muddy water that oozes down the compacted areas quickly fills the mountain streams and rivers. Not only does it flow away into oceans through the concrete tiled streams and regulated rivers lined by high levees, it also floods out towns and cities. Judging by the huge quantity of muddy water in our rivers, we try to compensate by building even higher and stronger levees, or reservoirs and polders. However, it is imperative that we start with the flood prevention measures in the mountains, because the drained mountains already struggle to maintain the functions that are crucial for sustaining life on planet Earth. We decided to do an experiment and create slopes in several areas in a forest without compacted soil in the older vegetation. We divided intact soil over the edge of a slope into 4 test fields, 1 square meter each, as high as the double height of the slope. We simulated 200 meters of rainfall at a speed that ensured the water gradually infiltrated the ground without runoff. The simulation lasted up to an hour. We collected the water that the disrupted capillaries discharged in a test field within 3 hours in receptacles. From the overall volume of 800 liters, the soil absorbed 239 liters, and the remaining 561 liters, or 71.1%, flowed out through the capillaries. The discharge of the rainwater from the severed capillaries in a slope depends mostly on the height of the man-made slope, its grade, and the soil composition. In another test field, in the same mountain situated in an area without a man-made slope, we simulated a 200-meter rainfall within 3.5 hours. Once the simulation was over, we dug in and found the water oozing out from capillaries 40 centimeters deep. In other test areas of clay and stone composition, the simulated 200 millimeters of rainfall infiltrated within an hour. Then we dug in, we found no trace of water. During this year's spring floods, some sources claimed that there was not a single river catchment in Slovakia that could contain 200 millimeters within 24 hours. I agree. River catchments contain intolerable amounts of compacted soil or soil drained by the disrupted capillaries in man-made slopes. I estimate that the drained soil over a slope is 3 times the width of the compacted soil under the slope. This drawing illustrates the compacted soil in black, empty capillaries in a man-made slope, and drained soil over the slope in brown. During the floods in 2010, some scientists acknowledged the fact that approximately 0.5% of the forest soil was compacted. After the flood near the town of Pila in 2011, a team of specialists led by Dr. Orfanus from the Slovak Academy of Sciences found that there was a 10-kilometer area of compacted soil on 1 square kilometer. They focused on forest roads, forwarding paths, and log yards. At an average estimated width of 4 meters, the compacted soil took up 4% of the area. That was 10 times more than what the scientists acknowledged in 2010. Circle number 1 depicts 100% of forests, with the estimated 0.5% of compacted soil. The drained soil takes up 3 times as much, or 1.5%. Circle number 2 shows the results of soil compaction measurements. I detected 7 to 10% of compacted soil with a GPS next to dried up forest streams. Graph number 3 illustrates the drained area in the forests, which takes up approximately 40% and keeps growing. When I arrived at these conclusions based on my experience, I started asking myself the following questions, intent on finding the answers. Question: why does it rain less in summers than it used to several decades ago? Answer: because the overhead air that rises from the landmass tends to keep the clouds coming from the seas and oceans out. Local vaporization over landmass that is systematically depleted of water has been dwindling. Question: when the clouds manage to reach the landmass, why do they tend to accumulate over the mountains? Answer: the hot air that rises from the overheated lowlands keeps the clouds out over the cooler mountain areas. Question: why was this phenomenon not noticeable 40 or 50 years ago? Answer: in the past, the lowlands were not drained by the man-made canals. In summers, the air that was rising up was saturated with water vapor from the soil, which also made it cooler. Drainage canals in the lowlands. I was born in the lowlands between 2 rivers, Ondava and Laborec. There were no drainage canals around them. In the late 1960s, a 4-meter deep canal at Sliepkovce was dug out among the first ones in eastern Slovakia. In the first year, the water level in the canal was 2 meters high. In the second year, when we were net fishing, the water level dropped to 1 meter. When I returned many years later in 2012, the canal was completely dry and overgrown with trees. I discovered that just between Ondava and Laborec, drainage canals running hundreds of kilometers were put in. The construction of canals disrupts capillaries on both sides, and they discharge the water they contained. Disrupted capillaries, much like the drainage canals, cause the surrounding fields to desiccate down to the baseline of the canals. After the heavy autumn rains, I measured the influence of the 3 canals on groundwater in an old well between December 2012 and May 2013. The measurements were taken at the lower end of the main K1 canal before its outfall at 101 meters above sea level. When the measured water level in the canal at Sliepkovce was at its highest and the water from the stream called Dusha spilled out onto the fields, just 15 kilometers upstream of the canal and the stream at just 5 meters above sea level higher, the canal was nearly empty and the stream was merely half full. Other tributary canals were only partly filled in the upper parts. In winters, the water in canals, much like the groundwater, would rise and fall. During heavy spring rains, the rhythm of rising and falling sped up 5 times. The recorded measurements have shown that the 15-kilometer canal unequivocally affects the groundwater levels and its tributaries along its entire length. Water drainage in the lowlands is similar to the process in the forest, but there is one difference. This process started over 50 years. Looking at the warming trend of the atmosphere since 1860, I ascribed the steep rise of the temperature aberrations between 1950 and 1980 to the lowland drainage canals. Something analogous is happening in the forests. Rigorous use of the conveyor belt and wheel logging equipment since its boom in 1980 has produced a sprawling network of forest roads and forwarding paths. We have already started experiencing the impact. The diagram of truth. With regard to the trend of rising atmosphere temperatures and the trend of falling river water levels, the correlation with soil compaction, marked in black, and soil drainage, marked in brown, becomes apparent. If we did not channel the rainwater over compacted soil and disrupted capillaries, would landslides be so frequent? Would the river water levels keep dropping? Would the underground water levels be dropping? Would the streams keep drying up? Would the forests keep drying up? How about nature on the whole? No! Our landscape would not desiccate and the landmass would not overheat. If the overheated landscape were not warming up the atmosphere, would the icebergs keep melting? The ocean water mass in the southern hemisphere is 14% larger than that in the northern one. If the ocean levels rise in the north, they do so in the south as well. Larger ocean mass means millions of tons of water more. Does the planet's center of gravity shift? How does it affect the Earth's rotation? What other disasters can this phenomenon cause in the future? Unchecked increase of soil compaction and man-made slopes spells disaster. It triggers the process of landmass drainage before the water can fulfill its vital function when the planet faces the sun. Landmass is desiccating from overheating, and the world is up against rising temperatures and more frequent weather fluctuations. I have come up with a solution to avert this trend and alleviate the negative impacts. The solution is instant, simple, and sustainable. I tested and tried the proposed interventions in 2011 in 2 eastern Slovak locations. I focused on defunct forwarding paths, ruts carved by heavy machinery, and compacted soil, and I decided to decompact them transversely with excavators along the entire length and width from top to bottom. This way, the pits dug out by the excavator would retain the rainwater. When the pits were freshly dug, the rainwater would take even longer to seep in. It means that the water created channels, new capillaries, and infiltrated the ground to reach the plant roots, springs, and groundwater. When I returned in spring 2013 to observe the decompacted soil, I found water in 15% of the pits at most. In the other pits, the soil took in the water immediately, much like an intact forest soil. If there were man-made slopes less than 2 meters high over the compacted soil areas, we ripped them to a depth of approximately 1 meter, so the water oozing from the capillaries could gradually infiltrate the decompacted soil in the slope and the dugout pits. The Slovak Academy of Sciences put the capability of decompacted soil to absorb water effectively to the test. The experiment was conducted on an eroded road formerly used for transporting timber. The scientists simulated rainfall with the intensity of 100 millimeters for 3 hours. The measurements showed that whilst the compacted earth hardly absorbed any water, the decompacted path retained 100%. How to resolve issues relating to man-made slopes. Man-made slopes over forest firefighting paths and haul roads that serve to truck the timber out of the forest can be treated in the following way. We decompact the soil 1 meter in width and approximately 2 to 4 meters in depth along the contour line, approximately 5 to 20 meters over the man-made slope. The water discharged from the disrupted capillaries will seep in the loosened soil and gently reach capillaries in deeper soil layers. How to resolve issues relating to lowland drainage canals. I propose small concrete barriers with an opening to be installed in drainage canals that allow the regulation of water levels in canals and, by extension, groundwater levels. I put this technology in practice in 2010. After 2 years, these measures proved their validity and functionality. These shots were taken in the dry summer season of 2012. The water level in the canal and the well 100 meters away match, which means the canal is integral in maintaining groundwater levels and replenishes the wells. While the canal is empty, the water level in the well 70 meters away is 24 centimeters higher. The dried up canal gradually drains the water from the well until both water levels even out. I took a number of measurements in different places. All of them proved that there was a correlation between the water level in canals, wells, and groundwater. Wherever the canals were regulated well and managed to retain water, the wells nearby were not short on water. Their water levels seemed stable. However, canals without water are detrimental to the groundwater system because they slowly drain it. Simple solutions are often most effective. Paradoxically, they are often the most difficult to gain public recognition. We tend to underrate ideas, which are right under our noses and they align with nature. Instead, we are drawn to complicated constructions and to speculations about too much rainfall or global warming, which we supposedly cannot influence. I am convinced that just as we can harm the nature on one hand, we can help it on the other. We can carry out thousands of small and financially undemanding interventions with immense final effect. Let us retain water where it falls. Let us stop unchecked water drainage and landmass desiccation. Reasonable and simple solutions are innate to nature, and they can minimize disasters. Please give them a chance. I did, and you can too.